My dear students, in today's class, let me explain to you iteration and recursion in Unit 2, Chapter 8. The subtopic invariance will be discussed briefly in this class. So, after completion of this chapter, you will be able to understand the concepts of variance and invariance used in algorithmic techniques. So, in the previous chapter, we have discussed about algorithmic techniques like composition, decomposition, everything. So, this is also a technique or concept which can be used in the concept of algorithmic techniques. And after that, you can able to apply algorithmic techniques in iteration as well as in recursion process. So, you can able to apply all this concept, algorithmic techniques in iteration as well as in recursion process. In the first passage, there are several problems which can be solved by doing the same actions repeatedly. So, by doing the same actions repeatedly, you can able to solve a problem. First point, both iteration and recursion are algorithm design techniques. So, this you have to underline. Iteration number one and number two is recursion are two different kinds of design techniques. What kind of design techniques? Algorithm design techniques which can be used to execute the same actions repeatedly. If you want to repeat the action again and again, in such cases you can use this concept, either iteration or recursion concept. What is the use of repeating the same action again and again? You are doing the same action again and again. What is the use of that? So, they give an explanation here. Even though the action is the same, so if you do the action repeatedly, the action will not be changed because it is remains same. But each time we execute the action, we implement the action, the state changes. The action is same, but the state is different. So, that is the conclusion of these three lines. Therefore, the same action is repeatedly executed, repeatedly again and again executed, but in different states, in different criteria, in different condition it is executed. That is what they are coming to conclude, that the action is same, but the state is different. The state changes in such a way that the process progresses to achieve the desired input-output relation is called as a variant. So, coming to the next passage, iteration. In iteration, the loop body is repeatedly executed. In iteration concept, the loop of the body will be executed as long as the loop condition is true. So, according to the condition, first as soon as the control flow enters, the condition will be checked. So, after the condition is checked, if it is true, it will be executed again. If it is false, it will be come out of that particular loop body structure. So, that is the explanation. In iteration, the loop body is repeatedly executed as long as the loop condition is true. Each time the loop body is executed, the variables are updated. So, if the condition is true, it will be executed and the variable will be incremented, which means updated. For example, if I value is 0, so after the execution, the I value will become as a 1. So, that is the meaning of variables are updated. However, there is also a property of the variables or the attributes of the variables which remains unchanged by the execution of the loop body. So, the variable will be updated or changed, incremented, but the property of the variables, it won't change. It will be remained unchanged by the execution of the loop body. This particular process or unchanging property is called the loop invariant. So, this can be asked in one more question. So, you have to underline this. This unchanging property, what unchanging property? The variables are updated. However, there is also a property of the variables which remains the same, which remains unchanged. Those unchanged property of the variables called as a loop invariant. Loop invariant is a key to construct, it is a key feature to construct or to design and to reason about iterative algorithms. So this is an important key feature, which is loop invariant is a key feature which is able to construct or design and to reason about iterative algorithms. And coming to the second main topic, recursion. First we have discussed about iteration, and second thing is recursion. Recursion is another algorithm design technique. So it is also a kind of algorithm design technique which is closely related to this concept. What concept? Iteration concept. And coming to the right hand side, but more powerful. So under this I am reading now. So this will be explained to you after completing this 4 lines. So recursion is very similar to the iteration concept, but it is more powerful. Using recursion concept in algorithmic structure, we solve a problem with a given input. So by getting the input, you can able to solve a problem with the use of this concept recursion. By solving the same problem with a part of the input, the same problem can be solved only with a part of the input, and you can able to construct a solution to the original problem from the solution to the partial input. By getting the partial input, you can able to conclude or you can able to solve the original problem. So that is a major feature of this particular concept, recursion. So that is the only difference between iteration and recursion. So look at this do concept. E.W. Dijkstra, so the name of the person you can see in the picture, was one of the most influential pioneers, which is influential person of computing science in the department of computer science. He made fundamental contributions, very basic contribution in the diverse areas such as programming language design, number 1, and number 2 is operating system, and number 3 is program design. In 3 areas he gave a very much contribution. He made fundamental contribution in programming language design, number 1, and number 2 is in operating systems, and number 3 is in program designing concept. Also he coined the phrase structured programming, a concept called structured programming, which helped lay the foundation. This particular concept, it is lay the foundation for the discipline of software engineering. For the progress of software engineering, this concept has helped, the structured programming concept. In the year 1972, so he was awarded as ACM Turing Award, which is a very most prizeable award in computer science, which is considered the highest distinction in computer science. So ACM Turing Award is considered as the very highest distinction in computer science department. This person is attributed to have said computer science is no more. So computer science concept will be no more about computers and astronomy. So he is comparing this concept to the astronomy concept, which is about telescopes. And coming to the next concept in page number 147, right hand side, 8.1, invariance. So this example clearly explains the concept of invariance. Invariance in the sense unchanged property of the variables, which we already discussed in the previous page. So example 8.1, suppose the following assignment is executed with u comma v. So 2 variables, one is u, the other one is v, 2 variables. These 2 variables assigned with the values 20 comma 15. So probably value 20 will be assigned in the variable u and 15 will be assigned to v variable. So we can annotate this, we can explain this before and after the assignment. Look at this before. So this 2 dashes shows you that it is a comment. So you have to ignore, the system will ignore while executing this particular algorithmic statements. So before the assignment, it is assigned like this, u comma v equal to 20 comma 15, where u will have the value of 20 and v will have the value of 15, and this is the assignment. After that they are incrementing 5 to the u and they are decrementing 5 to the v value. So here 5 should be added to the u value and 5 should be subtracted from the v value. So after this input, look at this, u comma v equal to 25 comma 10. How it has become 25 comma 10? Because we added 5 with the value of u. So 20 plus 5 will become 25. 15 minus 5 will become 10. So after the assignment 25 comma 10, but what do you observe about the value of the function u plus v? So before the assignment u plus v equal to 20 plus 15, it is the sum of this is 35, and after the assignment, even though you have given input something like adding 5 and subtracting 5, and after the assignment also if you add this u plus v, you will get 35. Since before the assignment the same value we got, and after the assignment also we got the same value as 35, the assignment has not changed. So this you have to underline, you have to listen carefully. So this particular statement only explains to you that it is an invariant. The assignment has not changed. The value of u plus v, we say that u plus v is an invariant of the assignment, because before the assignment the sum of the value is 35, and after the assignment also the sum of the value is 35. That is why it is called as a loop invariant or invariant of the assignment. So we can annotate, we can explain before and after the assignment with the invariant expression. Look at this. Before, so before the assignment u plus v is equal to 35, u comma v which is assigned to u plus 5 and v minus 5, and after the assignment it is 35. So look at this, before the assignment the value is 35, and after that also the value is 35. We can say u plus v is an invariant. It is 35 before as well as after. Or in other statements we can say that u plus v equal to 35 is an invariant because it is true before as well as after the assignment. So in the same way, the second example also given here, 8.2, if we execute the following assignment with p comma c equal to 10 comma 9, after the assignment u comma v is equal to 11 comma 10. So look at this example. Before the assignment, what is the value of p? 10. The value of c is 9, and after that we are giving some input. P comma c is assigned to p plus 1 and c plus 1. 1 is added to this value, p value, and then c value. So after this the value will be, so 10 plus 1 what will become 11, and 9 plus 1 obviously 10. So can you discover an invariant in this assignment? So can you able to identify invariant in this statement or in this algorithm concept? What is the value of p minus c before and after? So looking at this statement, you have to observe and you have to discover an invariant. First you have to look at the value of p minus c before and after. So p minus c equal to, so what is the value of p? 10, written here, minus, and what is the value of c? 9. So 10 minus 9 is equal to 1, and after that p minus c is equal to, so this is the exact value. After the assignment this is the value actually. So if you subtract 1 from 11, what will happen? So 11 minus 10, now this is p value and this is c value. So 11 minus 10 is equal to 1. Look at here. So before the assignment the value is 1, and after the assignment is also the value is 1. So that is why we can conclude that we find that p minus c is equal to 1 is an invariant in this algorithmic concept. So in general, if an expression of the variables has the same value, so this is an important line, listen carefully. In general concept, if an expression of the variables has the same value before as well as after the assignment, then it can be called as a invariant. So you can see in the right hand side. So before as well as after the assignment, it is called as an invariant of the assignment. So let p of u comma v be an expression involving variables u and v. So this is an expression you can conclude. So u is a variable and v is also a variable. So p of u comma v can be written as u comma v assigned to expression 1 and expression 2. So written E stands for expression. So which can be obtained from p of u comma v by replacing u by expression 1 and v by expression 2 simultaneously. Simultaneously in the sense at the same time. So P of u comma v is an invariant of assignment, so which is assigned to the value of expression 1 and expression 2. So look at this example, P of u comma v, so which can be assigned like this, u and v. So u will be taken as expression 1 and v will take expression 2. So that is why briefly explained as P of u comma v. And coming to the third example, example 8.3, show that P minus C is an invariant of the assignment. The same example which we discussed in the previous previous page number. P minus 1 is an invariant of the assignment. Look at this, P comma C assigned to P plus 1 and C plus 1. For example, the value of P is 10, the value of C is 9, the same concept. If you look at this, let P of P comma C equal to P minus C. You have to prove like this. Then you have to write like this, P of P minus C, which is assigned to P comma C, assigned to P plus 1 and C plus 1. So if you do like this, if you simplify all this expression, you will get P minus C. So which will be this plus 1 and minus will be go inside. So this will become minus 1, you can strike out. So obviously P minus C will be the remaining. So this is one more example for this concept, and there are more example related to this one. Just go through all those things, the remaining examples, which is comes under the category of m plus n. And coming to the next concept, 8.2 loop invariant. So left hand side 8.2, the concept we called as loop invariant. In a loop, if L is an invariant of the loop body. So in this concept, in a loop structure, if L, the first letter of loop, L is an invariant of the loop body B. So loop body structure, body from the B letter, then L is known as a loop invariant, while C in the sense condition, the condition is true. So it is denoted as a command line loop and body of the loop and then loop structure. The loop invariant is true before the loop body and after the loop body, before, after. So two kinds of loop bodies are there. Since L is true at the start of the first iteration, L is true at the start of the loop also. Since L is true, I mean the loop body structure is true at the end of the last iteration in the sense the last execution, L is true when the loop ends also, just after the loop body. Thus, if L is a loop variant, then it is true at 4 important points in the algorithm. One is at the start of the loop, which can be considered as a before the loop, and the second one is at the start of each iteration, each execution, which is considered as a before loop body, and the third one is at the end of each iteration. So end of each iteration in the sense after loop body. So and then in the same page number 149, the fourth statement is at the end of the loop, so which can be considered as a just after the loop. So these are the 4 kind of explanation for this loop invariant concept, and this is a flow chart given here. So here double dash L, which is considered as a command line double dash, this is the start of the loop, and after that they place the condition, while condition, and secondly this concept is called as a start of iteration, the first level of execution, and this is considered as a body of the loop structure, and thirdly this one is end of iteration, at last end of a entire loop. So you can put into this in flow chart like this, where inputs the first parallelogram, the parallelogram shapes explains to you it is an input given, and after that L denotes here first start of loop, you can see in this flow chart, and this is which is in the diamond shape, we placed a condition. So according to this condition only this loop structure will be iterated, and this one is we call it as a second start of iteration, and this one is which is a body structure end of iteration, and this last one is denotes it is end of the loop. So this is a brief explanation. So, when you see in a diagrammatic level, you will able to understand easily. That is why they have given in the flow chart also, but the same concept, same explanation. Now, how to construct a loop? Construct in the sense how to design a loop. So, there are steps given here. Number one is establish the loop invariant at the start of the loop. So, first you have to establish, you have to accomplish the loop invariant at the start of the loop. So, that is the foremost thing. The second thing is the loop body should so update the variables. The variable should be updated as to progress, as to execute, as to process towards the end, as well as to maintain the loop invariant at the same time. So, these are all the rules you have to keep in mind while you are constructing the loop concept. Number one is establish the loop invariant at the start of the loop. Start of the loop in the sense beginning of the loop. The second point is the loop body should so update the variables. The variable should be updated or incremented as to progress towards the end. And thirdly, it has to maintain the loop invariant at the same time. So, it has to be, the variables has to be updated. And number two, it has to maintain the loop invariant at the same time. So, that is the second point you have to keep in mind. Third is when the loop ends, end in the sense when the loop concluded, when the loop comes to the end point, the termination condition, the end of the condition and the loop invariant should establish the input output relation. It should establish, it should show the relation between the input output properties. So, that is the third thing. So, these are all the 3 points you have to keep in mind while you are constructing a loop concept. And coming to the next page number 150, 8.3, invariance, the examples given here. Look at this. The loop invariant is true in 4 crucial points in a loop. The loop invariant is true. The condition will be true in 4 crucial points, 4 different points. Using the loop invariant, we can construct, we can design the loop and reason about the properties of the variables at this point. So, you can able to construct the loop as well as you can able to reason about the properties in the sense attributes of the variables at these points. Example 8.5, design an iterative algorithm and compute an, let us name the algorithm power of a comma n for example. So, you have to find out a comma n, power of a comma n. Look at this example, simple examples. Power of 10 comma 4. What is the meaning of this? So, 10 into 10 into 10 into 10, 4 times you have to multiply. So, if you multiply 4 times, you will get 10,000. So, that is the value. And coming to the second example, power of 5 comma 3, which is 5 power 3. What is the meaning of that? 5 into 5 into 5, 3 times you have to write. So, 5 into 5, 25, and 25 into 5 you will get 125. And the third example, power of 2 comma 5, which is 2 power 5. So, you have to write 5 at the top, 2 at the subscript. So, if you write like this, 2 into 2 into 2 into 2 into 2, 5 times you have to multiply. So, if you multiply like this, you will get the value of 32. So, this is a simple example which can be used here to design as well as an iterative algorithm to compute an. So, using the 2 different variables. So, briefly they will explain the iteration table also here on the right hand side. Look at this. So, this is a table, iteration table. So, here before the iteration starts, so this is 0 level, no. What is the value of p? 1. So, p into a, nothing is here. What is the value of I? 0. I plus 1, nothing is here. This is the initial state, and a power 1 is 2 power 0. Anything power 0 is equal to 1. So, this is the beginning. And in the first level of iteration, so this is the first level of iteration 1. So, here the value is 2 and p into a, so which is 1 into 2. And what is the value of I? I incremented from 0, which is 0 plus 1. What will become 1? So, that is how written here 0 plus 1 and here 2 power 1. On the second level of execution, it is written like this. So, what is the value of 2 power 2? So, it is 4. So, P value is 2, 2 into 2, second level of iteration. What is the value of I? So, here 1, 1 plus 1 again incremented 2 and here 2 power 2. So, like that it goes on up to 5th level 1, 2, 3, 4, 5. So, 5th level of iterations. When the loop ends, this particular execution ends, P is equal to a power 1 is still true, but I is equal to 5 here. So, I is defined as a 5, therefore, P is equal to a power 5. So, in general concept, when the loop ends, P is equal to a power n. Thus, we have verified that power of a power n satisfies specifications. So, that is the example explained in 8.5. And coming to the next example, 8.6, the same concept. Recall the chocolate bar problem of example. So, as small or bigger one, chocolate bar, dairy milk or 5-star or whatever it is. So, consider like that. Recall the chocolate bar problem of example 1.11. How many cuts are needed to break the bar into its individual squares? So, to make it as a individual squares, how many cuts are needed? So, this is the assignment, this is an example given here. We decided to represent the number of pieces and the number of cuts by variables. So, number of squares we are representing by a variable and number of cuts also represented by a variables. Look at here, we decided to represent the number of pieces and the number of cuts by variables P and C respectively. So, whenever a cut is made, the number of cuts increases. So, when you cut like this with the use of fingers, the square shape chocolate will be increased one by one. So, as soon as you cut and keep it, the pieces will be increased as well as the cut also will be increased. So, that is what they have discussed here, where a cut is made, the number of cuts increases by 1 and the number of pieces also increases by 1. Very simple. So, when you made a single cut, a single piece will become this side. When you make a double cut, the next cut, one more piece will come. So, like that, whenever you made a cut, the number of cut increases by 1 as well as the number of pieces also increases by 1. We decided to model it by an assignment where P comma C assigned to P plus 1 comma C plus 1. The process of cutting the bar can be modeled. The process of cutting the chocolate bar can be modeled by a loop. So, we can take into consideration with the loop concept. We start with 1 piece and 0 cuts. So, P is equal to 1. Piece represents here 1 and C represents cuts. So, cut is 0 cuts and pieces is 1. Let n be the number of individual square when the number of pieces P. So, look at this example. So, where the chocolate bars can be individual squares by cutting the pieces of chocolates. P comma C, which is assigned to 1 comma 0 initial state, where the piece is equal to 1, cut is equal to 0, while P is not equal to n. This is not equal, not equal. P comma C assigned to P plus 1 and C plus 1. So, we have observed with the use of this assignment in example 8.2 that P minus C is an invariant of the assignment, because P comma C assigned to P plus 1, piece is also increased by 1 and cut also increased by 1. Let P comma C is equal to K, where K is a constant, it will not be changed. So, that is the meaning of constant. The points in the algorithm where P comma C is equal to K is true are shown in the algorithm below and in the flow chart of figure 8.2. So, this is an example of one more example of algorithm concept which comes under loop invariant. So, these are all the examples for loop invariant. So, look at all this example, the same examples for the concept of loop invariant. So, all this 8.10, so all the examples. So, you can see in the page number 153 also. A jar of marbles also comes under this category. And 8.4, the next very important concept, recursion. So, this concept will be discussed in the upcoming session. So, after listening to this video session, go through all the examples, practice well, read twice and thrice, so that you can easily understand. First, you have to read the definition for variant, loop invariant, and you have to clearly study about iteration and recursion. Only then you can able to understand the concept of this recursion concept and iteration concept. So, after reading all those definition, you have to look at the examples. So, look at the examples, and if you have any doubts, you can ring up to me or you can send a WhatsApp message to me between 7 to 8 p.m. so that I can clear to you. Thank you.